I would like to make a very general remark that his work was the core of my CDC plenary last December, made my life much easier in preparing a plenary talk for CDC. So I think that it's a remarkable achievement. Another thing that I'm particularly impressed and proud of is that he's able to make contributions in autonomy of robotic and autonomous vehicles, focusing across the entire stack of autonomy, and as well as the entire integration of those components into making our robots safer. And without any and also that he's not only working on the theoretical aspect, but also on the experimental aspect of the problem, as you see also some first clips of his videos there. And this is one of the quadrotors that he designed and built himself that we very affectionately in the lab call the dev quad, in his honor, I guess. And everyone is using that also for their research as well. So without any further ado, unless the committee has any comments that you would like to discuss before the presentation, okay. I would suggest that maybe you keep your questions towards the end. If there's something that really needs to be asked, feel free to interrupt, but maybe we can plan for a rather 50-minute talk and then have the discussion at the end. So.
Thanks, Prof. I will admit I have not timed myself on this, so we will see how it goes. I know Caleb is back there. He's going to give me hand signals on if I need to speed up and slow down. But thanks, everyone, for coming here. My name is Dev, and over the past 5 years, I've mostly been working with drones, other types of robots, and trying to understand how can we make them safer? How can we make them something that becomes a part of our everyday lives? And I really, really want to be able to use this technology to be able to help people in the future. I think understanding what goes on and how these things work is going to be really important. There are two main questions that I want to try and address during the course of this 50 minutes. These do sort of tie together, but for the purpose of this presentation, I'm going to sort of treat them separately. We can talk about how they fit together at the end. The first question is, how can we ensure safety? And I'm going to go through what that really means, but the question is, we have a robot that's operating in a really difficult environment. It's something that's dynamic, that's uncertain. How do we guarantee safety? The second main question is, what are the limits of information gathering abilities? So a lot of the times you're sending these robots out to do a certain task. In some cases, that is like an information gathering task. For instance, you want to collect the salinity, the air temperature, or whatever. That could be like a task that you want to do. And so now the question is, what are the limits of how quickly and efficiently can you collect that information? But it also ties into like safety aspects. For instance, if the drone needs to fly around an environment and it's a windy environment, you need to know how the wind is in the environment to be able to operate safely. So that's how these sort of questions were motivated. And I'll go through this in a moment. I want to say that the first part is basically going to be gatekeeper. This is an algorithm or an architecture that we came up with to try and think about safety in more complicated environments. And that's what I'm going to discuss there. And in the second part, I'm going to introduce clarity and perceivability. These are two metrics or measures that I'm introducing to try and characterize information. Why do we want safety? This is a story I came across in a podcast that I really love. But essentially, if you think about it, every day you use a lift, you walk into a metal box in a hollow shaft, and if the cable snaps, what happens? So historically, the rich people used to live on the ground floor because that was where you didn't need to take stairs to be able to get up to your apartment. But once the lift was invented in its modern form, people started moving up, away from the roads, away from the pollution. And this really was an enabling factor around the 1850s. What happened? Elisha Otis, which you might recognize from Otis elevators, was the one who first created the safety mechanism for an elevator. He basically created a leaf spring that was mounted inside the lift, where if the main cable snapped, the leaf spring would expand and grab onto the side walls of the shaft and make sure you only fall a couple feet and not actually fall all the way down to the bottom of the shaft. And so he demonstrated this by very famously being at the World's Fair in New York, where he got on his elevator, he cut off the rope to his lone lift, and he stopped. And I think that captured people's imagination. And I think what really inspires me about this story is he sort of built the safety mechanism into the product. The safety mechanism was built into it to the point where people could start to use it and really appreciate how how to, to be able to trust someone and trust Elisha Otis, I guess, on being able to use the lift. The question is, how does this extend to modern autonomy systems? In modern autonomy systems, we can't just do mechanical things. We can't just build, a parachute into the side of the helicopter and prevent it from falling or crashing. You need to be a little bit smarter about this. And so that's what motivates a lot of my research. What are the safety guarantees that we really want? I'm going to motivate this through two really simple examples. The first is subterranean navigation. You have this drone that's operating in a dark, dusty environment. It's trying to go through many obstacles. How do you get it to go from point A to point B without crashing into things? Even if it's teleoperated, there's delay and there's lag in how you communicate with the robot. You want some level of autonomy or safety critical aspects built into the robot. The second example is called a Firewatch mission, and I'm going to keep coming back to this one. It's a really common firefighting mission. Essentially, the problem is that firefighters don't know where the fire is in a wild firefighting scenario. You can get satellite imagery at some update rate. It's usually not very high resolution, and it's usually not real time enough. So what they do is they tell a helicopter pilot, go fly along the perimeter of the fire, as close to the fire as you can go, and we'll use the GPS trace to be able to figure out where the fire is. And then the firefighters figure out where they want to allocate resources. So the question is, how do we design an algorithm to replace the human in this case? Perhaps if you wanted to be able to fly this without sending the human literally into the line of fire. So what kind of guarantees do we want? Ultimately, we want to ensure safety. In the first example, that's like obstacle avoidance. In the second example, that's making sure the helicopter doesn't enter the fire. And you have other standard constraints. You want to respect the dynamics of your vehicle. You want to respect input constraints. You also want to make sure you finish the mission. It's a very easy way to stay safe. Just stay at home, don't go anywhere, don't do anything. But that's not the kind of safety that we want. And you also want to be robust to disturbances and uncertainties. These are going to be a core part of any robotic system that you implement. We need to understand how these factor into your system. For the purposes of this talk, what we really want is a mathematical guarantee. We want a mathematical guarantee that the algorithms that we put on our system will be able to respect the safety constraints and operate correctly as they operate through the environment. So how does one build safe autonomous systems? I think this block diagram really, it took me a while to realize that this was the block diagram, which is kind of sad, but essentially you have a robot. You have a robot that operates in some sort of environment. It spits out sensor data, and whatever the sensor data is, it goes into your autonomy stack. And all the code and all the algorithms you have lie inside this autonomy stack. It respects mission requirements, it respects safety requirements, and ultimately you calculate a control input. The only thing you can control is those control inputs. That determines the fate of the robot. And so we really need to understand what's going on. How are these control inputs calculated? Usually, a robotic system consists of three main modules, and usually here I've drawn them as one single line, but they're usually a little bit more interconnected. You have a perception system that estimates the robot state, that estimates the obstacles in the environment, depending on the mission. You have a planner that takes all of the mission requirements, that takes in the perceptions output and figures out a plan and a trajectory. And then you have the controller that actually computes what is the command that you're going to send to your motors or your thrusters or whatever you have there. And that gets sent into the robot. Let's talk a little bit about what these safety requirements usually look like. Formalizing the notion of safety a little bit, you should think about it as, or at least I think about it as a dynamical system, x dot equals f of x u, where x is your state and u is your control input. And you have a robot that operates in some sort of environment. The environment has some constraints. And so essentially this is, when I say safety, I really mean a set constraint problem. You're trying to guarantee some constraints are satisfied. Things like avoid the wall, stay out of the fire. These all form a safe set S. So S throughout this presentation is going to denote the set of states that you're allowed to be in at any given time. And so the goal is to ensure that you stay inside this set S. How do people normally achieve this safety? I think it comes down to a few different ideas, but one that has really taken hold of the research community in the last 10 years in particular has been to think about it as something that you apply at the very end of your autonomy stack, right? If the only thing that determines the robot's trajectory into the future is your control inputs, what if we just filtered the control inputs at the very end and made sure we never sent bad control inputs to the robot? So that essentially is an idea of safety filtering the controller. A lot of you probably recognize that this is the idea of control barrier functions. Control barrier functions were introduced by Professor Ames, where he considers this control affine dynamical system And he says, well, okay, so we have a whole lot of constraints, but let's say we can find a function h. This function h is kind of like a magic function, takes in your state and returns a single number. If it's positive, we consider it safe. If it's negative, we consider it unsafe. And so it defines the set C that's like a subset of your safe set. And what AIM says is, if H is a CBF, and I won't go into the technical definitions here, if H is a CBF, then he can define a controller, which we call pi CBF, and that ensures that if you started within C, you'd be able to stay inside C forever in time. And so if you can guarantee that H is a CBF, then you have all of these nice properties where you can guarantee safety. The fundamental problem, and I mean, we've worked a lot in our lab on control barrier functions. A lot of people around the world have also worked on these. But the fundamental problem seems to be finding a CBF is hard. It's computationally difficult if you want to try numerical methods. It's analytically often quite difficult because your robot dynamics are not so easy to work with. And so it becomes difficult to find a CBF. The benefit, of course, is that you can handle very nonlinear systems, or you can handle nonlinear systems as long as they're control affine. And so while you do get the benefit of the nonlinearity and like the handling of these constraints, you still need to find a CBF. So that was sort of the first idea, filter the control inputs. Something that's been like, since the dawn of robotics, perhaps, the way that people have started to think about this is, can we constrain the controller? We want to maintain constraints. What if we put these constraints into the planner itself and made sure trajectories were safe? And so what does this look like? There's many, many, many methods for doing this. I'm going to highlight two of them, broad classes. The first is path planning methods, where you use simplified dynamic models, usually kinematic models or single integrators, double integrator type models, and you plan trajectories that respect all your constraints. Obstacle avoidance, dynamic obstacles can be handled, sometimes Dubin vehicle type systems can be handled. And so you can handle a lot of complex and sometimes dynamic environments. But the problem is that you've got the difference in the model. You've got a model that you use for the planning, and you've got a model that your actual robot is. And in between, there's a controller that somehow should handle all of the mismatch. And that's usually not a well-studied, or some people have studied this problem, but it's usually quite tricky to take the trajectories that are planned by a path planner and actually put them on your robot as a control input. We did some work on this, trying to see how you can merge that gap a little bit, but it means that you need a lot of assumptions on exactly how these components are built together. Another common approach is model predictive control and all of its variants. Essentially here, you use the full nonlinear dynamics, or you use, in some cases, a simplified model again, and you plan a short horizon into the future. By planning a short horizon into the future, you can really think about what the robot's going to do over the coming horizon, and you can choose to act on the first little part of it and then replan at the next time step. This is really nice because you can really think about all your constraints, and you can enforce your constraints in your path planners as like explicitly. But one of the main challenges on a theoretical level is guaranteeing recursive feasibility and stability. These are two really important concepts that I did not appreciate until we ran our controller. Like, we ran an MPC controller and it didn't work. And I remember Ugo being like, yeah, you don't have recursive feasibility. Of course it's not going to work. Essentially what recursive feasibility says is, if my controller is able to find a trajectory at the current time step, I act. At the next time step, will it still be able to find a control input? You really don't want a scenario where your robots don't have this property, because halfway through operation, your controller would be like, I'm sorry, I don't know what to do. And then your robot fails. The other challenge with model predictive control is that it can sometimes be computationally challenging, especially if you have a non-convex problem, especially if you have dynamic environments. It can be really difficult to guarantee that your controllers solve within a fixed amount of time that's necessary to run this in real time. So these were like broadly the two types of methods that people have tried for guaranteeing safety. And what we're going to try and do is, I was thinking about the firefighting mission, and I heard about this from an actual helicopter pilot who flies this mission. He's like, how do humans achieve this? There's some way that humans achieve this. And so as I was talking to him, the main thing that he kept thinking about was contingencies, fail-safes, and backups. Essentially, as you're flying through the mission, can you recover safely? Can I go back to the landing pad? Can I do something to escape anything that's bad that's going to be happening? So the main perspective shift is, instead of trying to design a controller and a control invariant set and check all your conditions over all of C, what if we just checked that there was a safe trajectory going into the future? You just need to check that there exists a way for you to be safe into the future. And this is the main idea that Gatekeeper tries to build on. Also, we want to do this without compromising on mission objectives. So now I'm going to try and describe to you a little bit about how Gatekeeper works. The core idea is that you have some sort of safe set that you don't really know a priori because it's unknown. And you have a perceived safe set, which is the set of states that you can see with your robot at the current time. So that's going to be denoted by B0. All of this can be time varying, but on the graphics, it's more or less going to be static just to make it easier to understand. The idea is that you have a nominal trajectory coming out of your path planner that looks, that's over here. The nominal trajectory is coming out of the path planner. What Gatekeeper is going to do is it's going to take this perceived safe set, check whether things are safe, and if they are, it's going to create a committed trajectory. And this committed trajectory, I'm going to guarantee it's safe by construction, and that's the only thing the controller will ever see. So the controller only ever sees safe trajectories to follow. How does this work? At the kth iteration, we're going to construct a candidate trajectory using the path planner's nominal trajectory. We're going to check if the candidate is valid. If it is, we're going to commit it. And the controller is always going to track the last committed trajectory. Now, you want to be able to guarantee this for all time into the future, right? You want t for all t greater than tk. Of course, we can't plan infinite horizons. We can't compute infinite horizons. So what I'm going to do is I'm going to split it into a finite horizon and an infinite horizon. So the first half is going to split between tk to tkb, and then for the second half, tkb onwards. And a way to guarantee this is you check that the first half lies within your perceived safe set, and your second half enters something called the controlled invariant set. So C over here is this small little set that I've drawn over here. It's a set that you know how to stay safe in. It could be hover, it could be go back to the runway, any sort of controller that you know that once you enter the set, you can stay inside it. And so the idea is essentially if we check the trajectory for a finite horizon into the future, that's the first half, tk to tkb, and we check that we are able to reach the C set, then you know that that trajectory is one that is safe for all time and that you can follow it. I'm going to show you exactly how we prove that in a moment. This is essentially a recursive guarantee of safety. So you need a first committed trajectory, but after that, you can keep updating your committed trajectory and moving along your mission. So now I'm going to walk through exactly the scenario. Our robot starts out at T0 over here, and it's trying to follow this nominal trajectory. It doesn't see the hidden obstacle at the top. It can see a part of this obstacle, and it's trying to move out this way. It's just some sort of like constraint set in which it can see what's going on with the world. So the first step is to identify CK. So I've drawn CK. Second step, we construct a candidate trajectory. To construct a candidate trajectory, what we do is we choose a switching time. For the first part of it, we try and track the nominal trajectory. For the second half of it, we try and apply the backup controller. And what this allows us to do is it allows us to see what will happen with the trajectories if we try to follow the nominal for some amount of time. You know, we really want to do what the mission wants us to do. And so what we're going to do is we're going to try and follow the nominal and then execute the backup. And we're going to check that that trajectory is safe. And so I essentially do a grid search of T0s, the switching time, and I see when is the last time that I can actually successfully reach the control invariant set safely. That then becomes the committed trajectory. So this is now the green committed trajectory that we can then send to the controllers for tracking. Right? We were able to find a trajectory that was valid, and therefore it becomes the committed trajectory. And as I've said, the controller tracks the last committed trajectory, so now time moves forward, and the robot moves from T0 to the next planning iteration with time T1. Okay, so what happens at T1? Repeat the steps. You find a new control invariant set, so that's now C1. You then try and construct a bunch of candidate trajectories to follow the nominal and also to get back to C1. And if you are able to find one, which it'll do soon, it'll be able to be committed. And so now you can see that it's tried to construct this, it barely skims this obstacle, and it says, okay, now I know that this is a safe trajectory for me to execute, I'm going to commit it. And so now that becomes the new committed trajectory, you can forget about the old one. Controller continues to track this new green trajectory. At the next time step, when it gets to T2, you try and construct a new control invariance at C2, and you try and find another way to be able to get along your nominal and back to C2, but you can't. The obstacle is too close. And so we are not able to commit a trajectory. So the committed trajectory is not updated. We continue to use the old committed trajectory. So the robot continues to move along the green trajectory outwards. So notice how by construction, we are maintaining that there exists a trajectory that is safe for all time into the future. It's all you need. As long as that one of those trajectories exists, you can stay safe. And as long as you can replan, you can keep moving along your nominal mission, and keep moving along achieving your mission objectives. I want to talk briefly about what are the kind of guarantees and what are the kind of properties of this system. And I'm not going to put up a formal theorem statement because that takes a paper. But essentially, Gatekeeper provides a recursive guarantee of safety, right? A guarantee of safety under nonlinear dynamics, multiple constraints, and input bounds. And all of this is achievable because when we construct our candidate trajectories, we are forward propagating the actual dynamics of the robot. We can impose all of our input constraints while we're forward propagating things, and so we can check that these things are happening. We can also check against multiple constraints because you can literally check if the trajectory is going to be safe along this. There are ways to optimize that, but at a crude level, you're just checking point-wise along the trajectory if you're safe. And we really constructed this to handle time-varying safe sets, time-varying dynamics potentially, and really the perceived safe set was the main thing that was really interesting to us. How do you handle scenarios where you don't know everything about the world and about the universe when you start? Can we still construct safe trajectories there? The other cool properties about this is it's very low compute cost. Compared to something like MPC, where you need to solve for all states, all control inputs over a finite horizon, and you're running an optimizer to be able to solve for that. In Gatekeeper, all you're doing is you're choosing the switching time. You know, you're forward propagating a few trajectories and you're choosing your switching time, so there's one scalar you're optimizing for. That makes it far more efficient computationally. And in the paper, we've shown how you can robustify some of these checks to disturbances and observer errors. Essentially, you build tubes around your trajectories, and you check that your controller has some tracking properties, some sort of input to state stability type properties. Now, what does it assume to be able to achieve this? The main thing is this backup controller. This is the thing that Prof and I have thought about many, many times. How do we find the backup controller? My argument has always been, for certain robotic systems, you know what this backup controller is. You will not be able to find it for all robotic systems. You know, if you're doing a self-driving car with two cars, they could sandwich you, and there's no way for you to be able to stay safe, right? But perhaps the backup controller is moved towards the shoulder. But then you need to check that that also is a reasonable thing to do for the scenario. So I'm not saying that it's always easy, but I'm saying for some systems, we can construct backup. And I think we've been thinking about ways to extend this idea, maybe of multiple backups. Maybe you're doing something else to be able to construct these backup sets. It also assumes kind of mild assumption that there's a tracking controller and one that you can forward simulate in time. So it's not really good at handling stochastic uncertainty at the moment. If you've got a whole tube of trajectories that go through, we don't really know how to handle that yet, but we'll probably work on it at some point. Some things that I like about it, it does not assume convexity of the safe set. This is something that would be important if you're doing MPC again. You need some sort of convexity in the problem if you want to guarantee anything about the global optimality. There's ways around it, but it's nice that Gatekeeper doesn't make this assumption. It does put a lot of the onus onto the nominal planner to be able to achieve the desired trajectories. Yeah, it also doesn't assume that the nominal plan is dynamically feasible. Again, because we're doing a forward propagation of the actual trajectory dynamics, if you have a tracking controller on something that isn't dynamically feasible, then Gatekeeper will check that and actually produce a trajectory that is feasible. Now, the idea of a backup is not new, right? It's not like I came up with the whole idea of a backup, but as we went into the literature and looked at what other people have done, there's like two ideas that have been kind of recent and really cool, and I think I want to talk to you guys about it a little bit. The first comes from Jesus Tordesillas. He produced this paper called Faster. Essentially what he does is he uses MPC to simultaneously plan for both the nominal trajectory and the backup trajectory. So here he has a robot that starts at A, it's trying to get to E, but this blue region is unknown. We don't actually know what the safety is there. And so what it does is it plans both the red trajectory and the blue trajectory simultaneously. One of the challenges is that because he's using MPC, because he wanted formal guarantees, he assumed linear dynamics, he assumed convex safe sets, or at least unions of convex safe sets, and it was necessary to be able to guarantee the recursive feasibility. Another really cool idea comes from Andrew Singletary from Professor Ames' group. This is much closer to the idea of filtering at the controller level. Essentially what he does is he forward propagates just the backup controller. He forward propagates the backup controller along a trajectory, looks at how close that backup gets to the unsafe set, and if it's getting close to becoming unsafe, he switches his controller towards using the backup. He has this mixing controller where he mixes the nominal controller and the backup controller. And in that way, what he's able to do is he's able to create like a continuous time guarantee of safety, where Gatekeeper does it in discrete increments. The whole idea of the safety and backup filters is in continuous time. It's a really cool idea, and it works pretty well for a lot of scenarios. But one of its main limitations is that it only checks the safety of the backup trajectory, right? If your nominal was a safe thing to do, but your backup is one that's about to collide. Why do we switch to the backup, right? We should keep trying to use the nominal. And that was one thing that motivated the construction gatekeeper. So how do these fit into the overall architecture? Foster tries to put it in the planner. Backup filters tries to do filtering on the controller. What I'm arguing is gatekeeper is sort of a module that fits between the planner and the controller, tries to merge these together, tries to do some sort of filtering here to make sure only safe plans propagate their way into the controller. So let's talk about just a brief set of simulation results. Here's the Firewatch scenario again, and the little lines that you see running around are 3 different controllers and the nominal controller. You can see that, so Foster, backup filters, and gatekeeper. Foster and backup filters were not particularly designed for time-varying sets, so I've modified them slightly to fit the spirit of their controller design, but they're all able to maintain safety, right? So all 3 methods are able to maintain safety, but the problem that gatekeeper tries to solve is, compared to Foster, it's much faster to solve compute control inputs because we're not doing MPC. And compared to backup filters, because we're not mixing between the nominal control and the backup controller at every time, we're able to follow the nominal trajectories much more closely. We're able to be much closer to the fire. We're able to fly much faster along the fire. We've also run experiments with the dev quad. So this is in lab where we have this drone that's trying to make its way from its start location towards a goal on this yellow box. It's never seen this environment before. It has a real sense on board, so it's able to sense the environment. It has an ORN on board, so it's doing all of the compute on board. The only thing I've told it from my ground station computer is try and get to the yellow box. And what it does is it uses a A-star type planner for the nominal trajectory. It then checks against the obstacles that it can see and the obstacles that it can't see to be able to make sure that the trajectories that it commits are safe trajectories. And what you'll see is eventually it tries to make its way around. I think you probably just saw Hardik filming over there. It'll eventually start to make its way towards the goal. One interesting thing that comes out of this is you also need to send some feedback upstream. So when you have gatekeeper running, and there's this gap over here, A-star loves to try and find its way through this little gap. And if you let it, it'll keep trying to go along that way. So what I needed to do is in gatekeeper, add a thing where if it notices that gatekeeper is the reason it can't go through a gap, it publishes a virtual obstacle. So you'll notice this sort of flow back upstream from the gatekeeper levels up to the planner so that you can achieve the mission objectives. That's a really interesting idea, and I want to explore it further, but we haven't quite had the time for that yet. I want to talk briefly about some of the cool stuff that people have done using this idea. We've worked with the guys at AFRL for a little bit, and they've proposed a problem that sounds a little bit like Top Gun. You've got this team of agents that are trying to get through a narrow environment where there are essentially weapon engagement spots that you want to avoid. The question is, how can you design the trajectories for the followers? And so we've been working on that. Now there are a few directions. Caleb has been using this for energy persistence. How do we ensure that our robot can explore the environment under energy constraints, but also come back when necessary to ensure that it can be charged? And Daniel's been extending the ideas towards budget constraints. So if you've got maximum visual odometry errors, how can we ensure that our trajectories maintain those error bounds? Also, one of the main things that I've assumed is that you have a perceived safe set. And for the purposes of the experiment that you just saw, I assumed the perceived safe set was sort of perfect. But no perception system is going to be perfect. And so one of the things that I've been really interested in is how do we integrate the perception part with the planner and the controller such that these guarantees hold across your entire autonomy stack, right? If your perception system is not working correctly, it wouldn't be able to guarantee safety. And so the first piece of work over here is on what I'm calling certified perception. Essentially, you've got visual odometry drift when you're doing state estimation. That means your maps are kind of corrupted, and therefore you won't be able to guarantee safety. And so how do we modify the mapping algorithms that exist so that we can guarantee safety in the sense of any trajectory that is executed will actually lie within the safe set? And so the idea that we proposed was, instead of constructing safe sets that are just unions of all the free space that you've seen so far, you can also deflate those regions based on how much visual odometry error you've accumulated. And here we've really used a lot of the Lie algebras and Lie group theory to be able to understand how much error is accumulated per step, and how do we create safe maps in the body fixed frame. The second work, which I think the video is playing, is this idea on observer controllers. So again, you've got state estimation error, especially from like a common filter or any sort of EKF. That state estimation error means you don't really know what the state of the robot is. It lies within some sort of ellipsoid, but you don't really know what the state is. So how do you guarantee controllers working well in that state? And so this work was really trying to understand how do we correct our controllers under this state estimation uncertainty. All right, so that sort of wraps up a lot of the safety considerations that I've been talking about. We're really interested in how these safety guarantees propagate throughout the entire system and not just either the controller or the planner. And I think you really need to think about all of these components together when you're designing controllers to be able to guarantee safety. I'm going to switch gears now towards talking about information and what are the limits of information gathering capabilities of robots. So here the scenario is, sort of, I mean, the Mars helicopter didn't really do any sort of exploration, but here are the two main motivating examples for this line of work. The first is the amazing guys out in Austria, for some reason, were really interested in mapping the weather across their mountains. And so for the past 20 years, they've been collecting data at a resolution of 30 minutes at like 500-meter spatial distances. And they've mapped out this entire region over here with a whole bunch of weather stations. Very expensive, very, very involved. The question was, can we do this with a team of robots that move around and navigate the world? The second, and this is really work with Professor Chris Vermillion, is trying to understand things like salinity. So here's a picture from NASA. Essentially, it shows you what the salinity is across the Atlantic Ocean over time. And you can see that it changes in space and it changes in time. Now, if you want a robot to go out there and collect the salinity measurements, you need to think about what are the most optimal ways to do that. Some places it's going to be worth spending more time because the information is changing rapidly, and some places it's not going to be worth measuring because either you don't care about the salinity there or because the salinity is not going to be changing in time. And here's a boat that Professor Chris Vermillion has, and we've been using. Caleb and Kevin have been running experiments out in North Carolina, literally collecting measurements on a lake and hopefully eventually in the Gulf Stream. And the question is, how do we move the robot around to be able to collect those measurements efficiently? So the problem, in words, is we have a team of robots exploring this environment, and they're trying to collect information, right? How do we control these robots to do this efficiently? And when we started to think about this problem, we ran into a lot of problems very, very quickly. The first is, what does efficiently mean? We need a metric for efficiency here. And then we were like, but what does information mean? And then we struggled to try and define how do we talk about the quality of information that we're collecting. And then we struggled even more because we were wondering, can the robots even collect this information? The information is changing in space and time. You've got the entire world that you want to try and map, but you only have 3 robots. Is it even possible for these robots to go out there and collect the information that you want? And so that led us to what are the fundamental limits of information gathering. And so I tried to simplify the problem, tried to move all of the complexity of mountains and wind. And I thought about a single robot that has some sensing range, and we care about a single point P. The single point P might have some information associated with it. For instance, the wind speed, the temperature, whatever you want. It's some sort of vector. I'm going to denote that vector with M. So our goal is to use the robot X to be able to estimate M, right? And the simplest model I could think of was we have some sort of dynamical system for our robot. Here it's still nonlinear. And we've got a very, very simple model for the M. It's changing in time, so we said M dot equals some noise vector W. We had a linear sensing model. Notice how the sensor measurements Y are C of X times M, so it's linear in M, and there's some noise V added to it. The C of X really determines whether the robot is able to make measurements. Imagine C of X equals 0 means you can't make measurements. C of X equals 1 means you're actively making measurements. You're within the sensing field of range. And the question is to design a controller to collect information. To be able to quantify this, what is the right metric for information? And from probability theory, from information theory, the standard answer is differential entropy. Differential entropy measures how uncertain you are about a particular random variable. It has some very nice properties, but it also has some properties that make it hard for robotics. In particular, especially for continuous random variables, differential entropy can be both negative, and it could span all of -infinity to +infinity. And if you have a variable that spans -infinity to +infinity, and you want to drive it towards perfect information, which is -infinity, all your controllers, all your optimizers are going to be like, no, I don't know how to do this. right? Because you really can't try and optimize towards negative infinity. So we tried to mess around with this a little bit. We came up with this term that we now call clarity. It's basically a remapping of differential entropy. And what it does is it remaps it to a scale of 0 to 1. 0 means you have no information. 1 means you have perfect information about the random variable. It's a random variable, so you can't really get to clarity of 1, but all the maths works out quite nicely even in those cases. The equation looks a little scary, but essentially for a Gaussian random variable, it comes out to a really simple form. It's essentially 1 over 1 plus the covariance of the random variable. And so this form becomes kind of easy to work with, and you can start to do some analysis on how quickly information is changing and what's going on in the world. Now, I introduced to you the dynamical system in the model that I'm using for the world, and this was very specifically chosen because this is exactly the structure that a common filter works well with. Right? The common filter assumes you've got some sort of linear stochastic differential equation, and you've got linear measurement model. And so in this case, you can use the common filter dynamics to measure the rate of change of the mean and the rate of change of the covariance of the random variable m that you're trying to estimate. Instead of using the covariance dynamics, if you map it into the clarity dynamics, meaning you basically use this conversion, q equals 1 over 1 plus b, calculate q dot, you arrive at this quite remarkably nice form. This algebra works out really nicely because what you see is as you're making measurements, let's say you're measuring it in time, your clarity might start out somewhere around 0. You've got 0 clarity about the random variable, and the random variable's clarity increases. But it doesn't increase all the way up to 1. It doesn't increase all the way up to 1 because you have some stochasticity in this system. The random variable itself is changing in time, so you can't get to perfect knowledge about what the random variable is. There's two terms in q dot. The first term is essentially the rate at which clarity increases. Right? The first term here, c squared over r, can be read directly off of the sensing model, and it's essentially a signal-to-noise ratio for the measurements that you're trying to make. The second term is this q squared. This capital Q comes out of your measurement, out of your environment model. This is essentially directly the stochasticity of the environment. And this very nice separation of these two terms means that it's quite nice for us to think about what is causing information to increase and what is causing information to decrease. We compared this to a lot of literature in coverage control, right? This whole field falls into dynamic coverage. In coverage control, a lot of times we've seen this sort of structure where q dot is some constant or some number times 1 minus q minus alpha times q. That's a linear model for q dot, which makes it very nice for analysis. But S and alpha were tuned heuristically. We never really had a good way to design S and alpha because the equation here was kind of heuristically driven. It has the same characteristics in terms of the shape of the curves. But if you think about how the information really changes and you use these clarity dynamics, you see that it actually follows the square. There's a quadratic term over here. And even though it's a quadratic term, this particular equation is kind of nice to be able to handle analytically. It falls into the broad class of Riccati equations, and there are a lot of mathematical tools to analyze this. So what did we do with this? We thought about, we have a robot, we have a point that we're trying to collect information about. We know the clarity dynamics. The first question that we tried to answer was, what are optimal controllers to go and collect that information? And that really led us to what we now define as perceivability. The core idea is you create this augmented system of the robot dynamics and the clarity dynamics, and you can think about how these two things are coupled. You can forget about your common filters, you can simplify all of that away, but now you have an augmented system that you can solve an optimal control problem for. The second is dynamic coverage, and I'll get to that in a moment. Let's talk about perceivability. Perceivability, we've defined kind of similar to observability and reachability. It's this property of this environment and of the system. We're saying that a quantity is perceivable to some level q star if there exists a controller such that q reaches q star within some finite horizon. And so here, perceivability really does depend on the interaction of three things. It depends on the environment model, it depends on the robot's sensing capabilities, and it depends on the robot's actuation capabilities. You can move through the environment and get to some point that you want to go to if that's going to give you more information. And I've told you that it sounds like an optimal control problem, and that's because it ultimately is. We're trying to get Q to reach some level. You can pose this as a reachability problem, solve for a value function, use all of the tools from reachability and Hamilton-Jacobi analysis to check whether a quantity M is perceivable. Here's an example of applying this concept. So you have an ocean environment, and the robot starts out over here, and if it's inside the green region, it is collecting measurements of, let's say, salinity. And so the the question is, what are the optimal control strategies to be able to get there? Now, because we've been talking about Hamilton-Jacobi, we've talked about reachability. Once you have solved for the value function, you can actually get an optimal controller out of it, basically for free. Of course, solving for the value function is difficult, but let's say you could, you then get a controller. So you can now solve for the value function, and the blue curve here shows essentially what the value function looks like for the single integrator system. What you can do is solve for you can actually run the controller, and what you'll see is this robot starts out over here, moves up, and it has to do these like circles of this environment. The region over here where it's sensing has too much of a current to be able to stay inside that region and collect measurements indefinitely. So the robot figures out that it has to go around and do loops, go to places with lower current, and then be able to come back and make measurements. If we now change the robot's actuation model to like a Dubin's boat, so you're controlling the heading and the speed, and you have the exact same sensing model, you arrive at a slightly different trajectory for the system. So here you can see really clearly that based on the robot's dynamics, you might need to do different controllers and different trajectories to be able to collect information optimally. And you can also plot the clarity against time. And what you'll see is that for the single integrator, you can collect information more quickly. The clarity increases faster than that for the Dubin's boat. And so under different actuation models, you can have different levels of perceivability. I'm going to go back to the dynamic coverage case. So in the perceivability, we were really talking about a single point. What is the best way to collect information about a single quantity that's in your domain somewhere? But for dynamic coverage, we want to cover the entire domain and make measurements across the entire space. So here I'm going to start to talk about how we address that. And this was my CDC 2024 work. Essentially, we've got a team of robots over here that are exploring the environment. And as they make an interaction with the environment, they're producing measurements of what in this case, wind speed is at any given location. The idea is to model the information, like the wind field over the entire domain, as a Gaussian process. What we need over here is we need some way to be able to estimate, if I make a measurement here, how does it affect the information somewhere else? And so some amount of continuity or some level of correlation is needed. We assume the world was represented as some Gaussian process. Gaussian processes have some computational challenges, but a really nice property is that they have this equivalence with stochastic differential equations. And this is well understood, even if it's not super widely known, at least there's some really nice algebra to convert a Gaussian process into a stochastic differential equation. And as it happens, for certain classes of Gaussian processes, you end up with a linear stochastic differential equation, and back comes common filters. So now that you have the stochastic differential equation, we can estimate the information over the entire domain using what we're calling a spatiotemporal Gaussian process common filter. That part is not my own work. We've extended it a little bit, but essentially it comes out of other research groups in this field. What the STGPKF gives you is two things. First, it gives you the environment estimate map. So it lets you estimate what the wind speed is over the entire domain. And it also gives you a clarity map. It tells you how uncertain you are about the wind speed at any given point. And you can use this now to be able to design controllers. What we did was we tried to quantify the clarity gain rate. So if I have a team of robots that are placed at some locations, how quickly does the clarity increase over the entire domain? We can quantify that using an actual function. We call it the sensing function. And from there, you can design coverage controllers to be able to maximize the rate of information gain. And I don't have the time to really be able to go into the maths of this, but there were two methods that we proposed. One, which was more of a direct method, directly optimized for the ergodicity or the coverage quantity that we defined. And the second, which uses the time required to be able to collect information as a method of designing coverage controllers. I want to show you the pretty plots. Here, what we have is the two different methods, the direct method and the indirect method. And this is the true wind speed. And you can see kind of that it's changing in time. As the robots explore the environment, they produce an environment estimate map, which is over here. And over here, you can see what the clarity is over the entire domain, also as a function of time. And if you look at the trajectories, they look completely different, right? The direct method has these kind of spindly lines that like move around and jitter around a little bit. And that's really because the sensing function is extremely sharp, right? The measurement that you make over here only gives you information about your local vicinity. And so if you want to collect information everywhere, you really do have to cover at a fine level. The second method is the indirect method. This is much closer to ergodic controllers. Ergodic controllers are really nice at covering a domain, and you can see much smoother trajectories that cover the environment. But what's really interesting is that even though these trajectories look completely different, the mean clarity deficit against time, and I seem to have missed the slide there, but essentially the rate at which the clarity increases in time is remarkably similar for both types of methods. I was not expecting that result, but I think it's worth investigating that a little bit more. I want to talk briefly about some of the things that other people have done using this concept. Kevin and Caleb have run real-world experiments with this. They've created a whole architecture around this to talk about how much energy you have, how much solar power is coming into the boat, where you want to collect information from, and also trying to quantify like some regions that you care about more than other regions. And then you're trying to design controllers to cover that environment. These are some real-world experiment data that they have. Caleb's also trying to extend this method towards handling non-stationarity. So right now we've assumed the length scales and the time scales over your entire domain are constant, but some regions might have higher rates of change. So for instance, if you're in a lake right around a corner, maybe the wind speed changes a lot more than out in the middle of the ocean where the wind speeds are roughly constant in time. And so if that's the case, then perhaps you want to spend more time near the shore where the wind is changing rapidly rather than out in the ocean. So he's trying to see if we can extend the coverage controllers to be able to do that. All right, I'm gonna start to try and wrap things up. There were two main questions that we were trying to address. First is about these safety considerations, and the second is about the information gathering abilities. And like I mentioned at the very beginning, these two are kind of linked. If you can collect information about the world, you might be able to do things that are more aggressive while still being safe. And that's definitely a direction that we're starting to look into a little bit more. But why did I find this so difficult? Designing safe autonomy systems was actually surprisingly difficult. And I think it took me a lot of time to realize that one of the main reasons comes back to this block diagram. In this block diagram, we always think about it as perception feeds information into the planner, which feeds information into the controller. And you have this sort of flow of information that's sort of going left to right. You have this, every quantity is computed and then pushed downstream for the rest of the modules to use. But if you think about safety, safety actually runs the other way. We have constraints on how the controller should behave to be able to guarantee safety. And that imposes constraints on our planner, and that imposes constraints on our perception. Sometimes these are not so explicit, as is usually the case. People usually design their perception systems to sort of be robust to any sort of changes in the controller. But sometimes you can also make them very explicit. So one of the papers that we worked on, we combined the planner and controller into like a single framework where some of the safety constraints from the controller were really pushed into the planner as explicit MPC constraints. We saw how that leads to safety of the combined system. So I think as we develop more safe autonomous systems, we should really start to think about how these safety constraints play between the different modules, and how should we design these so that they're flexible and that they can be interconnected between these modules. A few other closing remarks. One of the main challenges is this resilience versus robustness question. I've talked a lot about robustness in the course of my PhD, but I've talked almost nothing about resilience. Like if I wiggle this HDMI cable, you'll probably not be able to see my screen. That sort of resilience is what we need to start thinking about. How fragile are our robotic systems? I don't know what the right mathematical frameworks to handle this is, and I think Prof has ideas. But I think we got to start thinking about resilience as well. These mission requirements are also often really vague. I tell you I want to explore an environment, but it's not really in a form that can be manipulated mathematically, algebraically, and seen exactly where those fit into all of these three modules. I think we should start to build out that kind of algebra. Some of the things that we're going to need to be able to go forward and really make these part of our everyday lives: stochasticity. Almost exclusively, I've worked with bounded errors and boundedness assumptions because it's much, much easier. As soon as you go into stochasticity, you got to talk about Ito variables, all of this like crazy calculus. I try to keep things simple by thinking about boundedness. And there's many, many people who are trying to extend this towards stochasticity, and I'd love to be able to see how that works. We also need to understand our sensors. I think very often we assume the sensors are good. And I'm going to show you a 1-minute video so I can take a water break. This is Mark Rober, I think literally 2 days ago.
I'm going to try and trick my Tesla's autopilot into running through this Wile E. Coyote painted brick wall. Because unlike other cars that use sensors like radar or LiDAR to see, Teslas famously only rely on simple optical cameras for its autopilot. Now to a human driver, while that sort of looks convincing, the image processing in our brains is advanced enough that we pick up on the minor visual inconsistencies and we wouldn't hit it. And then a car with LiDAR will of course stop because it's just using a point cloud that detects a wall without seeing the painted image at all. So while my clever ruse is no match for a human or a LiDAR sensor, question is, can I trick my Tesla into running straight through that wall? Well, as a firm believer in the scientific method, there's only one way to find out. Turns out my Tesla is less Roadrunner, more Wile E. Coyote. Wow!
So I mean, this is a really fun video, right? But it shows you some of the limitations of sensors. And one of the things that I have faced consistently with trying to implement coverage controllers on this is I'm using a RealSense camera that can see straight through glass. And our building is full of glass. It would be really, really nice if we had sensors that could detect this, and there are sensors out there. But we really need to think about how that interacts with our perception system and how that interacts with our planners and controllers. How do we use those to be able to know what is known to be safe, what is known to be unsafe, or what is unknown? We need to balance those as we design these controllers.
I'm gonna try and
Okay. And like I was saying, I think we need better abstract tools to be able to handle mission requirements, safety requirements, and the interaction of many of these robotic systems. All of these systems have a lot of autonomy and a lot of smarts inside them, but if you don't know how to communicate between and across these modules, we're going to have a lot of problems in integrating all these systems together and operate in the real world. So that's sort of the main ideas that I wanted to get across. I think we're time for acknowledgements. I think the main acknowledgement is to Professor. Thank you so much. This has been an absolute amazing experience, and I've learned so much from you that I couldn't have asked for a better advisor. I think a really good example of that is not my first, not my second, I think my third paper, Safe and Robust Observer Controllers, full of red ink, and I have it here if anyone wants to take a look. The other thing that I'm really grateful for is all the travel that I've been able to do. Damon, I think you should advertise this a lot more. I don't know, when I started grad school, I didn't really know that I could travel this much, but it would be great to be able to. It's great, meeting all these nerdy people in socially awkward situations and trying to understand what they're working on. Thank you, my committee, for being here, for giving me all this advice, for meeting up at conferences. I remember Professor Tzoumas, you told me, why would I go to a talk? I can read your paper in 15 minutes, and if I can understand it faster, then you can present it to me, then it's a good paper. Then I want to read it. And I really like that idea. The whole point of the conference is to meet people and to get cool ideas from people. And so that's what I tried to do all throughout my conferences. I've also been advised by Prof. Vermillion, Professor Ames. We've had joint projects together, and I've learned so much from them. Professor Ames has this remarkable ability to take an idea you presented to him and repeat it back to you and make it sound 10 times cooler. I think that's a professor trick. I've noticed some other professors also able to do this. That's something that's really, really cool. A few of you probably know John Ho because I've told you all about him. Professor John Ho was the first advisor that I really had. He took in a high schooler, guided me for 10 months. I was sitting right next to him. And we wrote a really cool paper together. And I learned all about the entire process from coming up with experiments, doing the experiments, writing the figures, writing the captions. He never let me write the paper, but writing the captions and also getting the reviews back and writing a response to it. So I learned everything about that. Like I was introduced to the whole process by John Ho way, way early on. And I think that has really helped throughout my PhD as well. Mr. Terrence Drew, my physics teacher, I think literally I was looking at this picture. It is of a guy in a lift and he's trying to figure out what the tension and the forces on the human are. Mr. Terrence Drew is almost singularly responsible for me to be interested in physics, to be interested in science, and to get me where I am. Damon, none of the experiments would have been possible without you, all of the support, and I think another huge part is the cohesive environment that you've built for the entire robotics building. I really, really do like that. And I want to thank Rotor, where I'll be going and joining sometime soon. They have given me 6 months of mental peace of not having to look for a job. I think a huge, huge amount of acknowledgements should go to my family, to my friends, and all the other people that have helped me out here, all the dogs and cats in the lives. And I think it's been great to know everyone. 2 other very, very special acknowledgements. If Paul Erdos is to be believed, this is the source of all theorems. All of them live right here in this little blue canister where the coffee beans are. So the coffee machine has been incredibly useful. And of course, the Lara and Brian kitchen, where I've been very, very regularly attending, getting nourishment and getting rejuvenated to be able to work on things. So with that, thank you very much, everyone. That was my defense.
Thank you, Dev. I think it's time for questions from the audience.
Yeah.
So just looking at your that one task that you showed with like the so I noticed that you have all these drones flying around, and it looks like one of them got trapped by the fire. And you kind of alluded to path planning around dynamic obstacles. Is that something that Gatekeeper can help like prevent from happening, or is that like
That's a great question.
Sort of like time horizon, like your autonomy?
Yeah. So I mean, the trick. I'll just explain it in words. The trick with Gatekeeper is you want to be able to get to a controlled invariant set, right? If you can get to a controlled invariant set, you're able to stay safe forever into the future. Sort of by assumption, sort of by construction. What is the controlled invariant set in the firefighting example? So the backup controller that I designed was one where you fly perpendicularly away from the fire, right? You try as hard as you can to just fly perpendicularly away. And if you can get sufficiently far away from the fire, then you're able to stay safe because I assumed a maximum fire spread rate, right? And so even though I don't know exactly how the fire is going to spread, I have an assumption on the maximum fire spread rate. The reason things can get trapped is if you don't really plan far out in advance, right? So the one that got trapped is the MPC controller. The MPC controller plans over a finite horizon, and it checks that it has the ability to move out of the way of the fire that it can see within the finite horizon. To do this very, very correctly, you would also have to impose the get as far away from the fire as possible constraint. But the timing horizons and stuff like that didn't really work out. I think there's a way to be able to handle that and like impose that as a constraint on the MPC problem as well. I think alluding to your question on dynamic obstacles, what we need is a model for how the environment can change the time. So we have a safe set. I've been defining the safe set as S of t because it's a time varying safe set. And as long as you can forward predict what will happen to the safe set, then you can use these methods. There are other scenarios, for instance, the social navigation scenario, where it's very difficult to do this. You don't know how the humans are going to move, and you've got very tight, narrow environments where the safe set very quickly disappears, and then you can't really guarantee safety. No.
Thank you.
Yeah.
And you said that for the gatekeeping architecture, you assume sort of a perfect backup set thing.
Mhm. How
much does the sort of choice of backup set matter?
It matters a huge amount. And this is something that we've definitely struggled with, to try and understand like how should you design your backup controllers. I'll tell you practical answers. So for this problem where the robot was trying to navigate through the environment, it had a goal location and it had an A-star trajectory to go through. What I did was I placed the control invariant set as a stop and hover condition along this trajectory. And so we try and go as far along the trajectory as it can. If it needs to stop, it needs to stop. And then it starts to hover and it starts to look around, so it builds out the map a little bit more. Now imagine my control invariant set was go away, right? Don't respect the nominal trajectory at all, just go away. Then it's constantly trying to do this, right? And so you can very easily mess with the system in that way. And we've been trying to think about what are the conditions on the backup controller such that you don't get this kind of behavior. And we've started to work on it. We're not quite there yet, but there are some, we're trying to define like an optimality gap. If you use Gatekeeper, if you make this additional assumption on the design of the backup controller and the backup set, can we guarantee that it is optimal in some sense with respect to the system that you have? So we're getting there, but we don't fully have an answer. For a lot of the robotic systems that, like Caleb's worked on or that I've worked on here, it's fairly easy to design the backup controller from intuition. Yeah.
I'm curious about your clarity definition.
Mhm.
You motivated it as like a mapping from -infinity to 0, 1.
Mhm.
But why did you choose this particular mapping?
This particular mapping was after about a day of whiteboarding. It really, wait, let me find it. It's really all about this connection with coverage control. So if you look at how the covariance equations move, it's not very clear how it relates to coverage control. So this coverage control equations were the ones that we knew of ahead of time. We knew people modeled it in this form, and it has this property where it goes up, and then it comes down because of stochasticity, or if you're not sensing the environment. And by messing around with the equations enough, I came up with this expression for the clarity. And if you take the time derivatives, you get this really nice property out. I tried really, really hard to get rid of the square. I couldn't get rid of the square. And so I think that's like a fundamental part of how information is collected. There's some sort of quadraticness built into the rate of change of information. But the rest of the form looks really similar. You know, you've got the 1 minus q over here, you've got 1 minus q squared, q over here, you've got q squared over here. And so the structure was similar. It has very similar plots. So if you look at like this kind of plots for how clarity changes in time, it looks very similar to what coverage controllers would do when they're tuned heuristically. But of course, the shape is slightly different. Oh, and on that point, this equation, the q equals 1 over 1 plus b, that's specifically for Gaussian random variables. But the expression that is over here, this expression takes into account the differential entropy of the random variable. So that could have any distribution you want. For the specific cases of uniform, Gaussian, like the chi-square distribution, those kind of distributions, there are analytic expressions for entropy and therefore for clarity. Yeah.
Just curious about like what's special about the point date it like converts to, like what other factors it depends on. Like,
are you talking about this one?
Yeah.
So this yellow line is in the papers we've called it Q infinity. Effectively, this is the steady state common filter gain, common filter covariance, right? If you had a time invariant linear time invariant common filter, there would be some sort of P infinity, and that is what corresponds to that yellow line. Intuitively, what's happening is that when you get close to over here, your sensors are producing more clarity, but your stochasticity is decreasing clarity. And so Q dot is equal to 0 near there. And that's where it balances out and reaches this state. Most of the time, I've done simulations where clarity starts lower than Q infinity and approaches. But if you start simulations with very, very high clarity, the simulations will show you that the clarity decreases because you're not allowed to have that much clarity about a random variable. You know, it's changing in time. You can't know it perfectly. Yeah.
So thanks a lot for the presentation. You did a great job of abstracting away so many equations.
Thank you.
Maintaining the wow factor. It's funny that you showed the Mark Robert video and asked you about it.
Yeah.
And somehow I think eventually it boils down to the cost of the sensor, right? If I have a $100,000 sensor, it's pretty much expected that I'm gonna hit into the wall. So I was gonna ask you, is it sort of easy to like compose these different objectives into your gatekeeper optimization problem?
Is it easy to compose these other? Interesting. As far as the design of the robotic system goes, I don't think Gatekeeper helps you with that. I don't think Gatekeeper helps you figure out, should I take sensor A or sensor B? Perhaps you could run simulations through it and see, you know, how well does the system perform if I chose sensor A versus sensor B, and especially if you had a model for how much, what the perceived safe set was, right? Like in the case of the LiDAR, in the case of the camera-based system, you should not trust some parts of your state space. And it's very hard, especially in that scenario, to decide what is actually safe and what is not safe. I'm gonna tell you another thing that was kind of interesting and kind of related, and it goes back to this multi-agent WES problem, right? And so in this problem, you have a bunch of jets that are flying through, and these are all Dubin's vehicles, right? Because they have maximum turn rates and like the maximum G-force that they can handle as they go through. That determines whether or not these trajectories work. So if you can increase your maximum G-force, for sure you can do more aggressive maneuvers. For sure you can be much closer to your nominal trajectories. And so your control limits will very quickly show up in these simulations. And so I don't think it's like a very explicit way of like going from like objectives to design constraints, but there's like a whole simulation block in between, at least if you want to use Gatekeeper.
That's kind of interesting, right? Like, you talked about at the end of in your conclusion slide that it actually goes the other way around. You know, that
The constraints flow.
Constraints influence
Mhm.
the component before it. So if that were deterministically true,
Okay.
then you should be able to use the steps before to pick your sensors, right?
Very true. And there was a workshop at CDC called category theory and architectures for this kind of stuff. And that's where they're starting to get into this. They're trying to build out an algebra, in this case, using category theory to think about how these different modules interact and how constraints flow together. So there's a guy named Gioli, I don't know how to pronounce his name, but he has, well, there's a few different ideas, but one of them is for each module, you define like a set of guarantees or contracts where if you pass in certain variables, it'll pass out certain other variables. And then you can compose systems together and really talk about the design space of the sensors and of the equipment that you have. I don't know that algebra, and category theory definitely scares me. But I think people are starting to think about that. It's still very, very early stages. Like I was talking to a guy from Lockheed Martin, it's all super abstract right now. Just the way we have Lyapunov functions to talk about stability, at some point we might have more tools to talk about this kind of stuff, but I don't know yet. Yeah.
More questions from the audience? Can you check also online if there are any questions?
No, we're good.
No questions on the chat? Okay.
I
Then
have
it sounds like,
Oh, was there one?
huh? Oh,
oh yeah, hi.
Sounds-
This is Jeremy.
Okay.
Thanks for the talk, Dev. It was great. I just have a quick question on slide 29. How did you get C sub k for your trajectory calculations?
How did I get C sub k?
Yeah. So yeah.
So for instance, in the firefighting example, the C sub k is be sufficiently far away from the fire. So I define like a radius, and I say, if you're able to get far away enough, then you're able to be safe. In the case of the gatekeeper with the quadrotor, it was a small set around stop and hover. So this was really like using an equilibrium condition and using an LQR controller, you can define like a small region around stop that I said was my C sub k. Does that sort of answer your question?
Oh yeah, I just wanted to know the decision-making process of how you decide like where the C1 should be located, C2 should be located, etc. So okay.
Yeah, there's definitely some flexibility there. In code, I actually just like literally implemented what seemed like a reasonable thing for me. And we've talked about trying to optimize CK, try to see.
your next paper. I have plans for you.
So yeah,
Okay,
still to be
cool.
figured out.
Yeah, thanks so much.
Other questions, online or from the room? If not, let's give Dev another round of applause.
Thank you.